So how are you all doing today? Your day two? While we're getting the last little things set up on the AV side, how many are first-time strange loopers here? Oh, wow, look at all the hands. Welcome, welcome. Much like the keynote yesterday, I was my first Strange Loop was also in 2017, and I've also been obsessively talking about it since then. In fact, there are several people who I twisted the arms of to come this year in this room right now. So before we get started on my talk, I'd love for us to give a round of applause to Alex and the team for like over 10 years of running an amazing event. It's always been the highlight of my year, and I hope it so far it's continued to be. But like enough about them. Let's talk about me. My name is Marianne Bellotti. I wrote this book called Kill It With Fire about modernizing legacy systems. That's by and large what I spent most of my time doing, looking at really, really old, really broken, nasty computer systems and figuring out how to make them slightly less nasty and less broken. Depending on whether you count the hacking I did when I was 13 years old. I've been sort of programming for 20 plus years. And right now I spend a lot of my time independent doing consulting and a lot of corporate training actually on how people reason about, how engineers specifically reason about systems and model systems and things like that. And so these are the kind of things that when you do my kind of job, you hear a lot. I hear alarmingly often, we have this server, no one knows what's on it. No one knows what it does. We're afraid to turn it off. I also hear far too often, there's this one guy that knows how this code works and what it does, and like, hopefully he won't die or retire. This is kind of like the world when you do legacy modernization. So when I started getting exposed to formal methods, which is primarily what the Fault project is about, my first reaction to it was not what people normally get really excited about. I don't give a shit if a system is correct, because when I'm dealing with COBOL from the 60s and then like multiple layers of Java piled on top of it so we can slam some internet input into the whole system, I am willing to stipulate that that system is not correct, right? This is not a surprise to me that this system is correct. This is not like a question of like, can we verify this system? No, it's wrong. It's all wrong, right? And also this theory about like formal methods, using it to sort of describe the specification before you go into implementation, that's wonderful, but very rarely am I writing a system from scratch. Usually I have something already set out and I'm trying to sort of incrementally improve it into something better. And there is some degree of modeling that helps with that, but not really in the way the formal methods community advocates for. If you're thinking to yourself, well, like, why not just rewrite it all from scratch? There's a great book you should buy that explains exactly why you should, like, just recommending, like, you should just go into that, right? So the thing I do care a lot about is reasoning about systems, particularly complex ones, and what their behaviors are, what we think their behaviors are, what their behaviors should be, and what their behaviors shouldn't be. And formal methods is actually a really great tool for that. So I think a lot about this question as of late. How do people become experts in systems? Because I do hear a lot that there's this one guy who's like the expert in the system. And yeah, of course, all of my clients are like, it'd be great if we had two guys who are the expert in the system, but we've been in this state for like 20 years and we still haven't figured out how to get a second guy up to the same level of expertise. So this question of how people become experts and how experts think about systems is really relevant to the stuff that I do. And we actually know a lot about how experts think about systems from ergonomics and system safety and social science. So what an expert has that a novice doesn't have, or even an intermediate user sometimes doesn't have, is this robust library of mental models about what the system does and different types of behaviors and different types of situations and contexts. And when something goes wrong on a system, what the expert does is kind of observe these characteristics and try to match it to the closest mental model in their head. And then they run these kind of scenarios forward and backwards. Okay, this is the input I'm seeing. What are the outputs given that mental model? Or they may go, this is the output that I've seen. This is the failure I've seen. Given that mental model, what might have caused that failure? And this is how they do this kind of rapid deduction that we all think is like magic and wizardry, right? And so how do people build mental models? Well, we all know the answer to this. First of all, you start with this very thorough comprehensive documentation that's wonderfully written in plain language. And then, of course, you've mocked out all your dependencies, and you have an amazing development environment that you can run locally that works exactly the way production does. And then you have a robust suite of tests, integration tests, regression tests, unit tests, so that you can experiment on behavior and like make changes and all of that. And like I can tell by the laughter that like, yeah, this isn't really how it works, right? First of all, we don't generally have these things in real life software engineering. We aspire to them. We don't usually have them. But even when we do have them, this isn't actually the way people build mental models of systems. The way people actually build mental models of systems is by operating systems, right? So they spend some time actually doing the work of like managing the system and operating it, and then they have an incident and they panic and freak out, but the panic is all the learning coming into the body, right? So I have never disliked being on incident, like being on call or being in a command room, because like there's so much I learn about a system when something is going wrong. And like it's really a pleasant experience if you can embrace it in the right way. But this is how people actually build mental models. It's through operations. So a mental model is essentially a pattern that we use as an analogy. So a great example of a kind of analogy that we're talking about is a ship is to water, as a plane is to... Thank you very much. It's to the air, right? So if you understand the relationship that a ship has in its environment, then you can make sort of some deductive conclusions about the relationship that a plane has in its environment. Is it 100% accurate? No. But does it get you, help you narrow things down and sort of make some general conclusions in an environment you know nothing about? Yes. So these are the value of mental models. We form these patterns via abstraction, and the part that I found really fun is that we can communicate those patterns and abstractions via formal methods. And actually, when you talk to people who are really into the formal methods community, this is one of the first things they'll say, that all the fancy like execution and model checking is almost beside the point. You find a lot of the bugs and a lot of the insight just by trying to write the model or the specification in the first place and having to go and talk to people. So before we go deeper, I don't want to assume any baseline knowledge. What do we mean by formal methods? Does that mean we all program in bow ties? Like what exactly is the formal part of formal methods? And so the formal part we're talking about is Boolean logic, right? We were trying to prove the properties of a model mathematically using logic. And when we build a model, we can use that same model to sort of have different levels of interaction. We can use it to run simulations, we can use it to check things, and then we can use it to do what's called execution, but it's slightly different than the execution you might be thinking of. So just briefly, simulation is a scenario where I have a model, I have inputs, I give the computer the inputs on the model, and I say, give me the outputs. Show me what happens when you have these inputs. And the computer can turn around and go, okay, you've given me addition, and you've given me a 2, and you've given me a 3, and obviously the answer is 5. Great. Because we're doing this with logic, we do not actually need to give the computer any numbers at all. We can give them a set of variables and just say, I don't know, whatever. Like it's addition, there's an A, there's a B, there's a C. Run me a scenario in which like this is the relationship. And it can give you 2 plus 3, but it can also say, oh, maybe we want to think about 1 plus 4. That also equals 5, right? So simulation, in most cases, is kind of overkill. Right? If all you want to do is run a simulation, you're probably better off with Python because specifically in Falt's case, we're dealing with SMT models and those are MP complete, which means it is possible to write a program that never returns an answer ever. So like probably there's a lot of computational complexity there and like if all you want to do is run a simulation, you're probably better off just kind of doing it with a more traditional programming language. However, when you're writing a model to do something more like checking, more like execution, simulation ends up being really useful because it's our equivalent of like the print statement in the source code going like, shit, I don't know what this, I think this does the right thing, like please tell me if I'm on the right path. And so often we'll just kind of like run it as a simulation to see what the model checker thinks we've just expressed with our model. So then we get to checking. So if simulation is I give you the inputs and you give me the output, then checking is I give you the output and you give me the input. So I have this relationship where A plus B equals C. or not equal C, and I say I'm going to give 5, and I'm going to stipulate that there is no value for A and no value for B that will ever equal C. Well, that's absurd, and the computer very quickly tells us, no, 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 no. There are values for A and B that will equal 5, and here I can prove it to you. And so again, we don't actually need to give the computer any numbers at all. We can just give them the relationship and the variables, and it will give us a scenario in which our invariance is proven incorrect, right? And so usually what we're doing here is this example sort of implies is we're sort of saying to the computer, I believe that this is true about the system, now prove me wrong. And the computer goes, challenge accepted. We generally do it with a little bit more complicated things than addition. But this is what backs formal verification. So when people are talking about formal verification, they're talking about this type of interaction, defining invariance, and then having the model checker kind of look for conditions in which your invariants are violated. It's a good place to sort of clarify that rarely are we talking about models that represent the entire system. We're usually looking at specific interactions and behaviors that we think should be impossible on those specific interactions. And so this kind of using a computer in this way sort of helps us focus deeply on the requirements, because we really have to have these in-depth conversations about what properties should be impossible in the first place, what behaviors should be impossible, and like, why are they impossible? What about the system and the way it operates makes these things impossible? That brings us to symbolic execution. So we have simulation, which is I give you the inputs and the computer gives me the outputs. We have checking, which is I give the outputs and the computer gives me the inputs. Symbolic execution is I give you the inputs and the outputs, and the computer gives me the function that creates the outputs from the inputs. And so I will tell the computer there is some function for which 2 and 3 leads to 5, and the computer will respond back addition. Obviously, if you add these two things together, you get your 5. And as with the other examples, we do not actually need to give the computer any numbers at all. It can just do this based on variables. So this is kind of like fun black magic. And typically when we build models like this, what we're actually doing is we're defining every conceivable pathway through a state graph or a system, and then we're saying start from here, go here, draw a line through all of those pathways. We use this a lot in malware analysis and security engineering to figure out, can we break into this part of the system through any particular channel? It's super, super cool, but kind of difficult to conceptualize. So kind of sum up some minor points about logic here. Solvers tend to give you the first answer they find in the state space. That's not necessarily the best or most insightful answer. It's just the one they find first. There are lots of really good options that already exist in the formal methods community. I use a lot of Z3, which is an SMT solver, Alloy, TLA+, Coq. If you've ever any interaction at all with formal methods, these are probably somewhat familiar to you, at least by name, if not by playing around with them. And that leads to the question of like, well, then why would you write something new? Especially since there's so much academic firepower around these really great tools that already exist. Why do something like fault? And so, since I'm a person who works in old computing systems a lot, I tend to sort of reference things back to historical points. And there was a point in computer science where when you complained about the syntax of computer programs and how you didn't understand what they did, you got told, well, you're just not good enough of a programmer, you should learn assembly. And while this was going on, there was this momentum, this community of people who felt like, wouldn't it be great if like computer programs were actually like readable by human beings and comprehensible by human beings? And this is the high-level language movement that got going. And we know how that ended. And like everything that we do with computers today is sort of comes from this conflict, right? If we were still writing assembly, we would not have iPhones, we would not have the vast majority of the applications that we use on the internet. Developing high-level languages that allowed people to communicate with computers in a way that was more comfortable and intuitive to them sort of opened the playing field up to a lot of creative and innovative solutions. And I feel the same way about formal methods. The tools that currently exist, their syntax is very strongly tied back to the mathematics, in the same way assembly is very strongly tied back to what the actual computer is doing. And that's great. But when you sort of say like, hey, I don't understand what any of this stuff means, the response you sometimes get from some people is like, well, if you were serious about it, you just learned the math, right? And the most infuriating thing is they go, it's just high school math. To which I sometimes say, what high school did you go to? But in any case, I thought, like, well, what would happen if we actually kind of created a domain-specific language that gave people a little bit more of the expressiveness that they think about systems and then compile down to SMT? Because computers can do that, right? We can just compile down to what we want it to be in Boolean logic. We don't need people to do a PhD in applied math on the side. Caveat here, the math is really cool, right? Like, I do not want to discourage anyone from actually going deep on learning the actual math, because that has been a joy and pleasure for me the last couple years, is figuring out, like, what exactly are these people talking about. So do please explore the math if you're so inclined. But I was kind of curious about this idea of, like, what would people write and what could we write and what kind of reasoning could what kind of conversations could we have about the systems that we were maintaining if we had an expressiveness that was a little bit closer to how we actually thought about systems. Especially given that both how people reason about systems is so strongly linked to how they try to express themselves about them, and also because we know that the full benefits from this type of modeling comes from communication. It comes from talking to other people about what you think these behaviors are. So the more accessible our expressiveness around these models are, the better we're going to get that benefit from communication. In theory, at least. You'll tell me if you feel like it's right at the end of it. So some facts about fault. First of all, it's highly experimental, which means it breaks all the goddamn time. It's wonderful. Related namespace is the demon. Like, just really, really hate namespace. It is technically not a compiler, it is technically a transpiler. So what fault is doing, among other things, it's a domain-specific language, and it's compiling down to SMT-lib2, which means any solver that understands SMT can integrate with fault and can be used to execute fault. The small caveat there is that what I found out when I switched it over from Z3 into Yeezus is that some solvers actually format their results slightly differently. And so one of the things fault does is it parses the results and attempts to format it in a way that is a little bit more comfortable as well. And so there's some testing and integration work that has to be done there to make it like fully cross-compatible across solvers. But if you can read SMT, you can have it just to export the SMT and run it on whatever solver you like. There's additional stuff that I kind of added on top of the logic, because I work primarily in what end up being either distributed systems or web-based systems. And there's stuff that we care about in that world that isn't necessarily doesn't map really nicely to logic necessarily. The first one being probability. Like a lot of what I work on isn't really about, is the system correct? It's about, at what point does the system fail? And you can absolutely write a model that will tell you, like, this is the breaking point in which you transition from this state to this other state that you've identified as not great. But it'll often give you scenarios that are just so outrageous given like the day-to-day kind of data you see that they seem unrealistic. So it's useful to have the compiler also be able to tell you, oh yeah, and there's the nth probability that this will actually happen. Strings are Booleans in fault, and we'll get to that in a second. And then the output formatting ended up being a really big deal. And I would say the vast majority of technical debt on fault comes from me trying to figure out how to format the output in a way that made sense. So just summarizing, it's a domain-specific language. It compiles down to single static assignment and then ultimately to SMT. Its syntax is C-flavored, it's curly braces, and semicolons. I do love my C-flavored languages. Its base abstraction, the first one I started with, is the Stockflow model, which is from System Dynamics. It uses state charts as well. Again, strings are Booleans. More on that in a second. There are no lists, no sets, no maps for now. I realized that from the perspective of first order logic, saying there are no sets in my formal methods is essentially heresy. And so if you see someone stacking up some logs around a wooden stake later on in the afternoon, that's for me. But it just, at the time, it felt like, let's keep it simple. Let's not have collections of any kind. Let's just keep things in a relatively simple pattern. So hitting on this, like, what is a Stockflow model? So this idea of thinking about feedback loops as a matter of pools of resources and then functions that affect some sort of change on that pools of resource. And so your stocks are your pools of resources, and then your flows are the rates of these functions that are essentially implementing change upon your resources. So from a technical point of view, we can think of resources being like system memory, system storage, CPU, and then we can think of it various functions that increase or decrease that in our system, memory allocation, creating files and data, starting processes, so on and so forth. Then we also have a different set of functions that free them up, right? We have garbage collection, we have deleting files, we have terminating processes. So we can start to think about how our VMs are reacting and interacting with one another in this way of like pools of resources and then functions acting on those pools of resources. And then maybe we might build a model like this where we have like a queue of files, and for every file we pull off the queue, it triggers an allocation of memory so we can process it. And then we have some sort of defined heap size that when the memory gets to a certain point, it triggers garbage collection. So this is an example of a type of model we might write with like stocks and flows. And so this kind of format is a bit different than what you mostly find in formal methods because, again, we're not thinking about correctness so much as we're thinking about interactions and capacity and how that creates behavior. It's essentially an extension of control theory. The people who developed system dynamics, they wanted to apply the same rigor of control theory, but they couldn't really quantify on things they couldn't really quantify, like business practices. So they had a sense of like it gets bigger, it gets smaller, but they didn't really have like actual numbers for rates of change on this. And this was a way of sort of getting the same sort of rigor without having to quantify everything. And you can express a lot of different types of systems using this abstraction. So sort of where I started, it was like the base of how I wanted to build my models. And this is what it looks like in Fault. So we're going to define our abstractions. We're going to define a stock, and then we're going to define a flow. And then we're going to say that these two abstractions are connected together. And within these flows, we define the functions of actually how we change them, right? And then we have what's called a run block in which we sort of initialize the model. We say we've defined all these abstractions. These are the ones we're using for these abstractions. And then within that run block, we're defining the steps of the model. So in addition to having no sets and no lists and no maps, Fault doesn't have a while loop or a for loop because it's a bounded loop model. So the whole model is itself a loop. It runs a number of times and it follows these steps. And it looks at whether you ever invalidate a constraint in the course of the model. So this particular model would run for 4 rounds, and every single round it would repeat the logic within the run block. So before we get into the details of that, I want to briefly cover what is single static assignment because it kind of becomes a tiny bit important here. So assuming that you all know nothing about compilers, single static assignment is this idea of variables are essentially immutable, static. We don't change their value after we assign them. So what do? We want to change the value of a variable. Well, we create a new variable, and we put the value of the new in the new variable. So if we have a variable A, and we set it to 4, and then we want to change it later to 6, we say, okay, the value of A1 is now A0 plus 2. Right? And so this is single static assignment. It's done in compilers, and it's actually really useful in SMT because SMT really likes, like, we have a variable and you only have to tell you what its value is once. And so when we compile the model I just showed you, this is part of what Fault generates on the SMT side. So yes, SMT is in Polish notation. Are we all comfortable with Polish notation? Okay, a couple hands. Yes, Some of us have like lost weekends with Lisp. I get it. It's fun. But for those of you who never had a good time with Lisp, I feel sorry for you. The only thing you need to understand about Polish notation is it's just a change in the order that you're used to. So you're used to the operator being in the middle of A and B. In Polish notation, we pull it out in front, and then the parameters are afterwards. So in our run block, we have this weird pipe operator because this is what we call in system dynamics a bathtub model. And the bathtub model is like the hello world of system dynamics. When they want to explain what system dynamics is to people, they draw a bathtub model. The idea being your resource is a bathtub, your stock is a bathtub. And then you have a flow of a faucet bringing water into the bathtub and a drain bringing water out of the bathtub. And the model question becomes, does the bathtub overflow, right? Well, in a bathtub, in the scenario of we're running the faucet and we're running the drain, it is not step one, we fill the bathtub up with water. Step two, we drain the bathtub of water. These things are happening at the same time, which is somewhat complicated to do in logic. But what we're saying here with this pipe operator is that these two processes are running in parallel. We do not know which one completes first. And so what fault does is it does scenario one. Scenario one is that the water coming out is moving at a faster rate than the water coming in, and so this completes first, and the water coming in completes second. And scenario two is the opposite. The water coming in completes before the water coming out, so this happens first, and then the water comes out. And so obviously in the design of these flows, the kind of smaller you can keep them, the closer you get to like simulating actual concurrency. And then we have this lovely statement in which we're saying to the SMT solver, great, we have two potential outcomes at the end of this. Pick one, don't care which, figure out which one it is, right? And the important thing here is this water level 5. This is what's called a phi value. And when you're using single static assignment and you have any kind of branching logic, whether it be choices between two parallel processes like this, or more likely an if conditional, you are going to have variables change within that conditional block. You're going to be incrementing that count in single static assignment, and then you're going to come out of that block. And whether or not you took that branch or not, you're now at a sync on your count. So the phi value is the next iteration where you basically say, whatever we ended up with, dump that value in this phi value so that our count has evened out and normalized and we can move on. This is actually a lot simpler in SMT because we're asking the solver to make all those choices for us than it is in actual compilers, but que sera. All right, so when we run this model, this is what Z3 returns, right? So I run this model and it's like, great success, here are your results. And this is a lot of why the fault does so much processing on the actual like output side, because there are a couple things that are really difficult about reading this. First of all, the results are completely out of order for the variable definitions, and they can be in any order that Z3 feels like at the time. So you kind of have to hunt around to sort of see how variables are changing. And then the other thing is that sometimes it'll return expressions instead of values. So this one's not so bad because all it's doing is saying it's negative 15. So it's expressing it as 15 and then a minus operator. But it will actually return fractions sometimes, and those become very difficult to just sort of eyeball and figure out like, well, what exactly is that value that's been returned? And so it became very clear very quickly that this simple like writing of the model and then compiling down to SMT was not actually enough to build something useful. I had to be able to parse the results and then figure out how to express them in ways that were useful to people. And so there were a couple different things that I went through in that quest. The first of which being the easiest, which is just taking all of the state changes, first putting them in the right order, grouping them by the variable they related to, and then just putting them in kind of like a list. Okay, this is how this variable changes throughout the model. But very quickly, it became very obvious that this took situations where there were branches, where there were parallel things going on, and just flattened them out and didn't give you any insight about which one of them were actually relevant in the scenario or what was happening or anything like that. So this became very clear it was not going to work. And so the second thing I tried was actually visualizing it, because I am a huge fan of Alloy, and Alloy's great visualization of models. So I let's take a shot at what that looks like. And so this is an output into Mermaid.js. And there are lots of advantages. Now we see the branching logic is much clearer, and we know what the phi values are, but it doesn't actually show where the violation is. And also, I had really complicated feelings about something that runs on the command line, essentially just spitting out a bunch of mermaid.js that I guess you then copy and paste and like go to web browser to look at. So I felt like that doesn't work, and I wasn't really into building an entire like IDE for my pet programming language. So I moved on, and I thought, what if we made it look like an event log? And so this is what it currently outputs by default, where it tells you how the solver is initialized, all the variables, and then it also tells you where that state change happens within the model. It gives you kind of the scope. Is this something that happens in the global scope, or is this something that's happening in a particular function? It also then filters out the dead branches, so the ones that were not selected, we don't really need to know about those state changes because they have effectively not happened. So it then cleans it up in that way, and then this makes it much easier to sort of read through and sort of visualize what the scenario it's actually describing to you is. So, how much time do I have left? Oh, good, I have enough time. I thought it would be fun. Do you guys want to see and play with some more models? That was the right answer. All right, I think that's a good size on text, right? Everybody can see? Everybody in the first 5 rows. If you're sitting further back, just move up. I don't get it. So I want to go back to this statement I made that like strings and faults are Booleans, right? Because the reality of it is that anything that can be expressed in binary, you can express in SMT, right? Because it's Boolean logic. But doing string manipulation with logic programming is sort of like, I don't know what the point would be. I'm sure there's some amazing dissertation that explains to me what the point of that would be, but I don't know what it is, and so please forward the paper to me so I can learn. But there is something that I thought was really useful, which is when you're defining these kind of static rules, it's really nice to have kind of long-form descriptions of what that static rule represents. So this is what I use strings, how I repurpose strings, is that they are effectively treated and interpreted as Booleans, but I allow them to be defined as strings so that it's really clear to the human being that's reading the model exactly what that rule represents. And so what you're looking at here is a model I did of the White House's directive that all federal employees be vaccinated for COVID-19. And the reason why I chose this is two. First of all, executive orders tend to be relatively short and compact, and they have few dependencies. So this particular executive order is dependent on 2 other pieces of regulation, both of in the US code, the first one defining what a federal agency is, and the second one defining what a federal employee is. If you have had any experience with policy, then you will know that the dependency tree on an average piece of regulation would make node package manager cry tears of joy, right? Like, we put node projects to shame with our dependency trees. So they get very complicated and people get very confused by them. And so this is an example of how I might express the definition of what an agency is. And I now can import that into my model, and I can say, okay, I assert that everybody who is classified as a federal employee must also be vaccinated for COVID-19. And for some reason, caps lock is on. Okay, and so now I'm gonna ask fault, and I'm not going to screw up my typing, to run this model. And I'm actually going to run it in a specific format for static rules because then it'll make it pretty. Okay, so then what fault puts out is because it's a static model, it will essentially print out all of the string values and then tell me if those rules are true. There's a lot going on here. So it says, I have found a scenario in which COVID vaccination and employment status are not equal to the same thing. And what's funny about this is that I thought it would give me a scenario in which you didn't have to be vaccinated for COVID. It says, no, be vaccinated for COVID, just don't work for the government, and then everything's fine. Right? So I feel judged by my language compiler a little bit as a person who's done a fair amount of work for the government. But another fun thing that you can find when you start looking through what is true in this model is there are all sorts of fun, weird things in government regulations. So let's see if I can highlight it. Yeah, okay. So here, as it turns out, did you know that the US Navy used to own a dairy farm? They don't anymore, but if you were an employee of that dairy farm before they sold it, like you may or may not be considered a government employee. I think you are considered a government employee. So it kind of helps you find like these strange edge cases within these kind of scenarios. But let's go back to like actual technical stuff. That's cute and amusing. And so I'm going to pull up this one, which is an example of a state machine. I talked about fault does state charts. And this was, I think, one of the most valuable pieces of syntax for me as a person in model systems was deciding to do state charts. And so what this is kind of like a system for buying and selling tickets, like Ticketmaster. And I've defined a seat as having 3 states. It's either free for you to buy a ticket, to sit in it, it's on hold because you're in the process of buying it, or it's sold, right? And so I can now take this state chart, and within each state, I define the conditions and logic that determine where it moves to once it's in that state. So from free, it can advance to being on hold, and from on hold, it can advance to either going back to free because I changed my mind, or it can advance to going sold. And from there, I can now make assertions about the path through this state chart. And so, oh no, what did I just do? Okay. And so we can run this. Tickets 1, tickets system. And what it's going to tell us is that it has found no case in which our invariant has been violated. Excellent, great. So it does this because I have an assert statement, which means that I'm checking instead of running simulations. If I comment out the assert statement and I run it again, it'll then give me a scenario. It'll like, okay, this is a thing that could happen in your state chart. You could transition here and here and here and here and here. And so that's all fun and cool, but not particularly useful. So let's add a little bit more complexity to it. What if, I'm gonna click this in, okay, great. For a second, I was worried it was gonna shut down the whole editor. What if we started to bring in a little sense of time? Because realistically speaking, when we do these kind of ticket sites, right, you can't be on hold, you can't be holding a seat forever, right? You have a certain window of opportunity in which you can transition from on hold to sold, or you lose the seat. And so we're going to use the Stockflow construction to create a sense of time. We have a reservoir of a certain number of minutes, and then we have a timer that ticks down those minutes every time that function is hit. And then from there, we go back and we have a very similar state chart to what we already had, except we change some of the logic on the on hold. And we say, okay, check to see the timer. If it's less or than or equal to 0, it can only advance to free. You got to free up that seat. If it's not, then it can either stay where it is or it can advance to sold, right? And then we can define assertions based on the behavior of this model. And now, when we run this one, I'm just going to change the 2. It finds a scenario in which that's not true. And so it defines the value of our pool of resources as being exactly 1 minute with exactly 1 round. And then it says, well, if you start from the state of a free seat, there's absolutely no way for you to get out of being on hold in that 1 minute that we've allotted per round. And so I think I have time for 1 more. And so I have 2 options. We can either go back to the bathtub model and look at a bug that I found in the compiler, or we can talk about dependency graphs. Bug or dependencies? Oh man, all right. You guys don't want to see my bugs? What's wrong with this? This is like, I'm on stage, prone to be humiliated, and you all don't want to see my bugs. All right, fine. We'll do dependencies. So this is something I've been playing around with recently because I kind of really want to do Boolean lattices. And so I've been looking at how do we do different types of graphs can we express different types of graphs, right? So I'm going to start from the specification. What I did is I took a list of dependencies. Think of it as your requirements text, and I basically created this stock called node where we have all of the dependencies that we could be using in this project. And then from there, I have the actual instances of each node in which I say, okay, this is a node, now these are the dependencies that are turned on. And what I can do from here is now create assertions about what things are turned on and active in the system at what times. So I see people like, I can hear the rumbling of crowds moving. So I'm going to end it there. I'm going to say that fault is open source, and on GitHub, you will probably break it if you use it, but that's excellent. Just send me the spec that broke it, and I will then go fix it. And thank you so much for your time, guys. I'm more than happy to take questions. You find me later.